In this lesson, we are going to continue with some of the things that were introduced previously regarding the calculation of pH values. First of all, let's briefly review that pH literally stands for the power of hydrogen, which means the exponent on the concentration of H+ ion in solution. Please remember that if you see a pair of square brackets, that means that the number inside the brackets is the molarity or concentration in moles per liter. Now, there are several formulas that you are going to need to make sure that you are comfortable with. The first one is the calculation of pH. The pH value is calculated by taking the negative log of the concentration of H+. We also discussed that for any solution, the product of the concentration of hydrogen ion times the concentration of the hydroxide ion was always equivalent to the same value, which is 1 × 10⁻14. This number, 1 × 10⁻14, is called K sub W, which is called the equilibrium constant of water. We haven't discussed equilibrium really to any extent, and in honors chemistry it's really not a subject that we really delve into. All it means is that we're talking about a system that is able to make changes in the concentration of one substance or another because of the addition of something that would disturb the balance between hydrogen and hydroxide. That usually means that in pure water, when you add water, you add base, or you add acid to the water, it adds additional H+ or OH-, and the system makes some changes in response to those additions. That's all the term equilibrium really means. But regardless, all you're going to need to know is that the molarity of the hydrogen ions times the molarity of the hydroxide ions will always equal 1 × 10⁻14. Now, we also discussed that POH was a little less used, but still is available, and that would be the negative log of the concentration of hydroxide. Okay, the pH scale, which you learned about earlier, is really based on the concentration of hydrogen, but we can also say there's a pOH scale, which is kind of like the inverse or the reverse, if you will, of the pH scale. Now, the last piece of information or formula that's useful is when the value for pH is added to the value of pOH, they will always add up to 14. That comes from this expression here. If we took the negative log of this entire expression, we would end up with this value, with this equation here. Now, in this video, what we're going to do is we're going to concentrate on using these numbers, using these equations here, to actually do some brief calculations. So you will need your calculators out. Discuss the use of the log button, and you'll have to make sure that you remember how to do logs in your calculator. Okay, so let's look at some example problems. So let's say, for example, we have a solution with a hydrogen ion concentration of 1.95 × 10⁻⁴ molar. And we need to find, sorry about that, we're going to find the pH, the pOH, and the hydroxide ion concentration. We can find all three of these numbers from just one value given those four equations that we talked about. Okay, so the first one's easiest to find. That's the pH. You'll remember that the pH equals the negative log of H plus. So that means for our problem, the pH will equal the negative log of 1.95 times 10 to the negative 4. Now, one thing that we have not discussed is significant figures in pH calculations. Now, anytime you do a pH calculation and you take the log, okay, you are going to add one significant figure to your answer. Okay, so let's input this in our calculator. So we're going to press log of 1.95 exponent negative 4. Don't forget, don't use times 10. Use your scientific notation button, EE. Okay, and that would be negative 3.7099. But we're taking the negative log, so that's going to equal 3.7099. Now, this is 3 sig figs. I need 4 sig figs, so it's going to be 3.710. Okay, so how do we find the pOH? Well, if we use our formula that the pH plus the pOH equals 14, then if our pH value is 3.710 plus the pOH would equal 14, means we just need to take 14 minus 3.710, and that will be our answer. Okay, and that equals 10.29, which is the pOH. Okay, our last problem asks us to find the hydroxide concentration. If you have H plus and you need OH minus, the easiest way to do it is to use this formula. H plus times OH minus equals 1 times 10 to the negative 14. Okay, so our H plus is 1.95 times 10 to the negative 4 times the hydroxide ion concentration will equal 1 times 10 to the negative 14. So that means I'm going to divide both sides by 1.95 times 10 to the negative 4. Let's down a little bit. Okay, so that's how I set up the problem. It's 1 times 10 to the negative 14 divided by the H plus concentration. So don't forget to use your scientific notation button. So I'll hit 1 EE negative 14 divided by 1.95 EE negative 4 and that equals 5.13 times 10 to the negative 11. That's my hydroxide ion concentration. Okay, so that's one very common type of problem, and you're going to do some of these in your packet today. Let's look at another type of problem. This one's a little bit different. If we're asked to find pH of a particular concentration of hydrochloric acid. Now, For strong acids, the H plus will equal the molarity of the acid. If it was a weak acid, we would need percent dissociation. Okay, so for a weak acid, the H plus would equal percent dissociation times the molarity of the acid. Now, hydrochloric acid is a strong acid, so for this problem, the concentration of the H plus would equal 0.75. So the pH would equal the negative log of the H plus, which would mean the pH for this problem is the negative log of 0.75. Okay, so if we put that in our calculators, we take the log of 0.75, okay, and it would be a positive number because it's a negative log. We have to take the negative of the log. So that means the pH would be equal to 0.125. I'm going to add one significant figure because I took the log of the number. Just kind of a quirk. Okay, what if it wasn't a strong acid? What if I said, find the pH of a 0.003 molar solution of acetic acid? And I told you to assume 3% dissociation. This is weak. It's not one of the 6 strong. So I would have to take 3% and convert that to a decimal, which would be 0.03. I would multiply that times the concentration of acid. Because remember, weak acids, only some of the molecules actually break up and make H+. Most of them would just stay together and be acid molecules. So only 3% of them will make H+. So the concentration, so this is how many moles of actual acid molecules are in 1 liter, but only 3% of those will break apart and make H+. Okay, so the concentration of H+ equals 0.03 times 0.003. Remember, that's the concentration. Put that in my calculator, 0.03 times 0.003, that equals 9 times 10 to the negative 5. Oh, sorry, it's supposed to be a 5. Okay, so the pH would be the negative log of 9 times 10 to the minus 5. Okay, so if I took the log of 9, okay, that would equal 4.0. It's 4.0. Because this is only 1 sig fig. That's 1 sig fig, so that gets 2 sig figs. For bases, it's very similar. Okay. Except if the number of OH minus in the formula is not 1, you have to multiply concentration of the base by the number of hydroxides. So for example, if I had 0.3 molar KOH, then the concentration of OH minus would equal 0.3. But if I had a 0.3 molar magnesium hydroxide, since there's two hydroxides in the formula, the concentration of hydroxide would be 0.3 times 2, which would be 0.6. Okay, because remember, for every one magnesium hydroxide, you get two hydroxide ions that come off of it. Okay, so the concentration of hydroxide ions is twice the original concentration of the base. Okay, the other thing that you have to remember when you're doing some of the problems in your packet today, okay, the pH of a base, okay, means you find pOH using the concentration of base okay, then subtract it from 14. It's like a trick problem. Okay, so they say find the pH of this basic solution, and they give you the concentration. If you simply put the concentration of the base and think that's P, and you're finding the pH directly, okay, you're going to get the wrong answer. If they give you the concentration of the base, you're finding pOH, and then you have to subtract it from 14 to actually find the pH value. Okay, so for example, okay, if we're going to use this problem above here, okay, if we're going to find the pH of this potassium hydroxide, okay, we're going to find pOH using the negative log of 0.3, because it's one hydroxide, so the hydroxide ion is the same as the concentration. Okay, so you would take the negative log of 0.3, and that is 5.2, 1 extra sig vig. And then you'd have to take 14 minus 5.2, sorry, I think it's 0.52. 0.52. That makes more sense. So you have to take 14 minus 0.52, okay, and that means that the pH would be 13.48. Okay, so don't be caught up by a trick problem. Okay, the very last thing I'm going to talk about is something that is kind of a little bit of an above and beyond topic, and that is the hydrolysis of salts. Okay, there is no spot for this in your note packet, okay, because we have just finished up through, well, your note packet says acid-base titrations, which we are not going to have time to do. So you might just put this on the back page of your note packet. Okay. The hydrolysis of salts talks about the fact that when an acid combined with a base makes water plus a salt. Okay. So you should remember this from your neutralization reactions in the chemical reaction chapter. Okay. So let's look at the general form of that. So that means HA, remember HA is the general form of an acid, plus BOH, which is the general form of Arrhenius base, is the ones we're going to do, makes HOH, okay, which is the same as H2O, plus the salt BA. Now, hydrolysis of salt simply means that, okay, if we just took this compound all by itself, put it back in water, okay, it would dissolve, okay, and depending upon whether the acid and the base that created the salt are weak or strong, the salt itself will have some acidic or basic properties. So if we're going to call this the parent acid, and we're going to call this the parent base. Okay, because it's kind of like they got together and they made BA. Okay, this is our salt. Okay, now if the parent is weak, acid is weak, and the parent base is strong, right, that gives you a basic salt. Okay, so it's kind of like the stronger parent kind of gives its properties to the offspring, kind of. Okay? So the strong base overpowers the weak acid and the salt ends up basic. Okay? If you have the opposite, if the parent base is weak, the parent acid is strong, okay, that means that the salt that they make is acidic. Okay? If they're both strong, you get a neutral salt. Okay, so some of you are probably thinking, well, what about the weak acid, weak base parent combination? Well, hey, because weaknesses are kind of relative on a sliding scale, say, we would have to actually have some idea about, you know, how weak or how strong, okay, each of them are compared to each other. So we're just going to stick with these three combinations. Now, what you're going to have to do, and this is kind of the tricky part, is I'm just going to give you a salt. And you have to basically, remember the salt is BA, you have to kind of like do a little bit of detective work. It's kind of like I'm going to give you the products, you have to figure out what the reactants were. Okay, so, for example, let's look at the salt. Barium sulfate. Okay, if I give you a salt, I'm going to ask you two things. What's the parent acid? What's the parent base? And is this compound basic, acidic, or neutral? So what you do here is you just simply label it as BA. Okay? So this B is the positive ion, A is the negative ion. And then you go back and you look at the formula and you say, okay, the acid had to be H and A. Okay. And the base had to be B and OH. Okay, so you know that your acid here was H and SO4, and your base was BA and OH. Okay, well, This is sulfate ion. You can look at the back of your periodic table. And H is positive 1. This is hydroxide ion. And barium ion is positive 2. These are ionic compounds. So that means the formula is H2SO4. This is the parent acid. The formula for this one must be Ba parentheses OH2. Okay, so they came from barium sulfate, came from sulfuric acid combining with barium hydroxide. This is a strong acid. This is a strong base. Okay, so strong plus strong equals neutral salt. This literally means if I dissolve barium sulfate in water and I measured the pH, I would get somewhere pretty close to 7. That's what they mean by. Let's do one more example of that. Let's do NH4. And Cl. This is ammonium chloride. Okay, so this is the B part. This is the A part. Okay. This is HA. So that means this is HCl. The B part is BOH. That means this was NH4OH. Now, the tricky part, and the reason I'm showing you this example, is that this is not strong. You say, well, it's a hydroxide. Yeah, but this particular hydroxide actually came from NH3. It's the weak base. Okay, so anytime you see ammonium hydroxide as the parent base, that's a weak base. So that means that this is weak. Oops, sorry about that. I can't read that. This is strong. So now we have an acidic salt. Okay, that's what the last page in your packet is going to be. Please make sure that excuse me. Please make sure as you try these problems that you don't forget when you're trying to assemble the parent acid, the parent base, that you look at the charges on everything before you put it together. All right, good luck, have fun. See you guys on Monday.